Okay, I think everybody can see my presentation now. Great. So hello again. My name is Micah, and I'm an architect and a consultant with Aerospike's client services team, and I help our Aerospike customers design, deploy, and operate Aerospike. So today I'm going to talk about Aerospike's enterprise security and what an end-to-end deployment might look like in a secure environment, perhaps storing highly sensitive data or with specific regulatory requirements around data privacy and security. If you have any questions or comments along the way, go ahead and submit them as we go. I'll answer what I can with the time left at the end of the presentation, and we'll provide all the responses in our Slack channel after the session. If you're not in the Slack channel, you can find that in the Developer Hub in the buttons on the right-hand side. So to begin with, let me just do a high-level look at what a deployment looks like, and that'll help frame some of the concepts I'm discussing today. So on the screen here, you see on the left-hand side, we have developers building applications or back office jobs that store and retrieve data from Aerospike. In the middle, we have SREs or DevOps or DBAs managing an Aerospike cluster, which consists of some number of individual nodes. For today's talk, let's assume a hybrid memory or all-flash configuration in which sensitive data is being persisted to SSD drives. And then on the right-hand side, we have downstream systems which are ingesting, analyzing, or taking action on security events and log data. Think of your security incident and event management platforms like Splunk and ArcSight and QRadar and things of that nature. So the first thing we're going to get into is we're going to look at all of these connections to Aerospike from people and from systems. How do we secure the network? Then we're going to look at how do we control who and what can access this data, and how do we manage that within our existing enterprise architecture. And then don't forget, we're persisting this data on physical devices somewhere, and even in the cloud, there's still racks and servers behind all the magic. So how do we protect that persisted data from unauthorized access, and how do we reduce the attack surface? And then finally, we'll take a bit of a closer look in how we verify that all of this is working right. How do we get visibility into what's happening, and how do we look back at the past and you know, look at what has happened in the event that there may have been a breach. So first, let's talk about securing the network. This is one of those areas that people either loathe or love. So if you love talking about firewalls and security groups and ingress and egress, then you're in for a treat. Otherwise, hang in there. Once you grok a couple of key concepts, then it shouldn't be too painful. There are essentially 4 types of connections to worry about, and they're all simple TCP connections. So let's assume a least privileged access model in which all network routes are blocked by default, and we need to explicitly open up only what is needed. So this is opening up rules in the firewall or the security groups. So in the diagram here, notice how every application node, shown as the blue servers, opens connections to every Aerospike node, shown as the red servers. This is what we call a shared nothing architecture. All of the Aerospike nodes are identical in function and form. That means with regard to connections coming from the applications, it's as simple as applying the same firewall rules to every node for what we call the service connection. The IP addresses of the applications are allowed to open up the TCP connections to every Aerospike node on the configured service port. In this example, I'm showing the common convention of port 3000 for the service port. Next, there are 2 distinct types of network connectivity between individual Aerospike nodes. The heartbeat connections, shown here as green arrows, are handling the clustering protocol in the mesh mode. This is another simple TCP connection that every Aerospike node establishes with every other node. What that means is the IP address of every Aerospike node is allowed to open up connections to every other Aerospike node on the configured heartbeat port. The next is what we call the fabric connections. 2 arrows. This connectivity moves data between the Aerospike nodes for replication and redistribution of data, otherwise known as migrations. So this is the actual data that's stored in the database on these network connections. Yet again, every node opens a TCP connection with every other node. Just like the heartbeat connections, every node would have both an ingress rule and an egress rule, depending on whether it's acting as the source or the destination of sending that data. So this is really just applying the same simple ingress and egress firewall and or security group rules as before with the heartbeat. It's going to look identical except for the port. And finally, for deployments which are using our cross-data center replication, or XDR, there would be additional egress rule for shipping data out to a different data center or cloud region, and an additional ingress rule for receiving data from a different data center or cloud region. The XDR replication is done using the service port, just like applications. Therefore, when a cluster is acting as the XDR source, the egress rule is just like that of the applications. It allows every node in the source cluster to establish a TCP connection with every node in the destination cluster on that configured service port. For the XDR cluster that is the destination, the ingress rule there is just like that of the cluster accepting connections from application nodes. So that means every node in the destination cluster will allow incoming connections from every node in the source cluster on that service port. And that's it. So depending on your security model, it may be even a little bit simpler if there's more trust within some of these private subnets. But even if you're doing a very explicit approach down to individual IP addresses of every machine, it's still pretty straightforward because it is just replicating that same pattern on each of these nodes. So the second part of securing the network is about using TLS to encrypt data in transit and ensure connections are only established with trusted machines on that network. So we just looked at 4 types of network connectivity: service, heartbeat, fabric, and XDR. Here to use TLS on each of those types of network connections independently. So let's start with those service connections. The service connections support standard or mutual authentication TLS, also referred to as MTLS. Both modes encrypt the data in transit. However, with standard TLS, only Aerospike authenticates themselves to the application nodes. With mutual TLS, the Aerospike nodes authenticate themselves to the application nodes, who also authenticate back to the Aerospike nodes. So it's a two-way authentication. A bad actor that had found its way into the network somehow could not pretend to be an application node, nor pretend to be an Aerospike node without possessing the correct private key. When TLS is enabled on the fabric or heartbeat connections, these are the Aerospike to Aerospike connections, they will always use what amounts to a mutual authentication TLS. So once again, if a bad actor somehow breaches the private network, they could not pretend to be another Aerospike node in the cluster, nor could they decrypt any of the data transferring between these nodes without possessing the appropriate private key. Sorry, let me go back one slide. So if you recall that the XDR connectivity is actually just using the service connections, so the same as the purple connectivity in terms of the port and the firewalls that were opened up. Likewise with TLS, the source cluster is acting as the TLS clients, and that's just like the application nodes, and the destination cluster is acting as the TLS servers. So the source is using the service connections, and it is the client, and from a TLS perspective, to the destination cluster nodes. And I apologize again, I keep clicking too soon there. So now all of these connections are typically each configured to use the same server certificate as they're the same machines, but they can technically be configured to have separate certificates. Additionally, every Aerospike node can be configured to use the same certificate, which means the entire cluster has one certificate, or every node can be set up with its own unique certificates. So that gives us 3 dimensions to work with. Standard TLS versus mutual TLS on the service connections, individual or shared certificates on each type of connection, and individual or shared certificates on each Aerospike node. Obviously, standard TLS with a single cluster-wide certificate is certainly the simplest in terms of setup and management complexity. And if you've spent much time dealing with certificate lifecycle management, one certificate certainly sounds more pleasant to manage than dozens or even hundreds of certificates. And indeed, it is. But for organizations adopting more of a zero trust model, perhaps within environments dealing with highly sensitive data on networks which are deemed as untrusted, such as public cloud, then unique certificates on each node may be required. However, most enterprises are going to fall somewhere in between, or most use cases, I should say, will fall somewhere in between these two extremes. And the flexibility of Aerospike TLS configuration will allow it to be tailored to the specific needs of the organization, the environment, and the use case. So now we get into the slide I keep trying to show you. And I just briefly want to touch on Cypher Suites. A Cypher Suite is a set of algorithms that are used in various phases during the TLS communication. The protocol allows both the client and server to negotiate which set of these algorithms both sides support and therefore what they're going to use when they communicate with each other. Every TLS connection I described in the previous section can be configured as to what Cypher Suites are allowed and in what priority they will be attempted during that negotiation. I won't spend too much time on this today, but there are two things that I want to point out from an Aerospike perspective. First, unlike a internet-facing application, many Aerospike deployments are done in environments where the organization is in control of both the client and the server. So that means that compatibility with public clients like web browsers is not a factor, and the list of allowed ciphers can really be honed in to just those more current algorithms which provide the best security and the best performance. At the time of this presentation right now, that is highly likely to mean a Cypher Suite that is using AES encryption, which has hardware acceleration built into modern CPUs, and the Galois counter mode, or GCM, which is also typically outperforming the previous block cipher modes. So more often than not, you're going to be able to hone your Cypher Suite to one of the lists that use those. That's going to satisfy most security requirements, and things like the key exchange and what type of search you're using are really organization dependent. The second point I'd like to make about the TLS Cypher Suites is Aerospike is using OpenSSL and thus configuring Cypher Suites using that notation. This is recognizable by the use of hyphens shown in the top line here. And other tools and libraries like Java, and oftentimes a security requirement or a document that's providing guidance on what types of Cypher Suites to use in what situations might use something known as the IANA notation. And you can recognize this by the use of underscores, and specifically TLS underscore, and then the rest of the details of the Cypher Suite. So this is just a sort of call out that if you are receiving requirements or working in Java and you're familiar with one notation, you might have to translate it to the other notation when you're configuring Aerospike. Okay, so now that we've talked about network security, what about the actors using the system? Identity and access management is a huge part of any IT organization. Aerospike includes a fundamental framework for authentication and authorization built in, but it also integrates into your existing IAM infrastructure. So let's look at a couple patterns related to that. So both human users and applications will need to authenticate when connecting to the Aerospike database. You may be pretty familiar with the concept of a human having to authenticate with a database. It's the grant X to Micah on Y. But let's touch a little more on the applications needing to authenticate. As we discussed in the previous bit there, when we were talking about TLS, there was authentication, right? But that was about network security. Is this server allowed to communicate with that server? Is it authenticated at that network level? But now we want to authenticate the application running on that network so that we can later control what that application is authorized to do. In other words, we're not trying to determine whether that application is allowed to communicate. We're trying to determine what that application is allowed to do. And to do that, we need to identify that application. So we need that application to be authenticated. I'll elaborate on authorization in a minute, but let's look more at authentication. Which application is this? So right out of the box, you can enable Aerospike's internal authentication, which is shown here. Both humans and applications present a username and a password combination when connecting to the Aerospike database, and all the user management is done directly within Aerospike itself using our tools. This works for simple use cases and is a no-brainer to set up. However, Every organization has their own unique set of IAM requirements, and they're unique from organization to organization. Things like password policies and credential lifecycle management, multi-factor authentication, etc. The nuances and complexities of such systems is really best delegated to the purpose-built tools already established within the enterprise IT infrastructure. So Aerospike supports integrating into these systems through external authentication. In external authentication, Aerospike will delegate the credential check to the third-party system. In this case, depicted here in this middle view, Aerospike is integrated via LDAP. After successful authentication, Aerospike will use an access token to authenticate subsequent connections for the lifetime of that token, and then go back to the LDAP server as needed to re-authenticate. This is a very common setup for human users of the database, and oftentimes applications as well. However, with this architecture, the directory is in the critical path for the functionality of the applications using Aerospike. The LDAP directory may not be designed with the same availability, performance, or scale that the application is being designed for, so it may not be viable for all use cases. So now we can look at an architecture that combines both authentication methods. LDAP and the directory are still being used for humans to authenticate, but the applications authenticate using the internal system. Now this removes LDAP from the critical path of the applications, but it does present a different problem. Part of the role of the directory in the external authentication was centralizing the identity and access management, typically with a separate team from the application team that is doing that management. If users are managed directly in Aerospike, how are the credentials going to be provisioned, rotated, and revoked on behalf of those applications? How will the organization's policies and regulatory requirements be enforced? In smaller organizations or autonomous business units, this may not pose a very large problem, and it might just be managed by the application teams themselves. But in larger organizations, this often becomes untenable. This is where secrets management and dynamic credentials can help. Rather than the applications themselves having credentials to Aerospike applications, the applications query the secrets management system to obtain the credentials, often short-lived credentials to lower risk. The secrets management system then has the access necessary to manage the full lifecycle of Aerospike credentials and does so within the domain of that existing centralized identity and access management. With one of these three patterns that are shown here, we'll have established which user or application is trying to do something, and now we can authorize them to do so. So we can apply access controls to the human user or application by assigning them to Aerospike roles. The role can then be allowed a set of privileges. A privilege consists of a permission to perform some action along with a scope. So for example, the permission to read data at a global scope would be one privilege, and the permission to read data only for a specific set in a specific namespace would be a different privilege. This will allow for a least privilege access model in which any database user, be it a human or application, can be associated to roles that only allow the minimum access necessary to perform the function that they need to perform. So there's some hypothetical examples up here for Acme Corporation. And the first is this Acme IAM role. In this example, this might be that secrets management that we just discussed. This is a role that allows for creating the users, deleting the users, just managing the full lifecycle of Aerospike users globally across all of Aerospike. The next role depicted here might be a site reliability engineer, and they may be authorized to do things like getting server statistics and gracefully removing a node for maintenance, enabling different log levels, things like that. The third is a database administrator who can perform functions to optimize for the use case in the data model, like managing secondary indexes and throttling scans, adding and removing user-defined functions and things of that nature. But then there are these three other roles in this example, Acme App 1, 2, and the daily loader. And each of these roles were created to allow the application specific access to the data that only that application needs and scoped down to the function that they're performing. So notice that Acme App 2 role can read data from the set named App 2, and it can only read the data from the set named App 2 within the namespace NS1. It is not allowed to read data from the set that App 1 is writing to, and it's also not able to write data anywhere. So this is how you can set up some fine-grained role-based access control for users and applications. And finally, every role can be assigned a whitelist of IP ranges. These would be insider notation to do ranges, which allow database users associated with that role to connect from only that range. So this provides an even finer level of granularity on top of the existing network security that we've already talked about. So for example, maybe a handful of employees can all connect to the Aerospike cluster from their office in a private network, but only Alice and Bob can create new users, and they can only do so from their personal workstations. So a very specific subset of the overall IP addresses that are allowed to talk to Aerospike are now further restricted to this role that's performing this specific function. Okay, well now we have firewall rules in place, we have TLS encryption on the network, and we've set up authentication and authorization. So that means in terms of data protection, we're protecting data in transit on the network, and we've applied tight controls on who or what can legitimately access that data. But we still need to consider how we are protecting data in its physical location, sitting on a device in a data center somewhere, as well as continue to minimize the attack surface on the actual servers. For that, we're going to look at protecting data at rest, OS hardening, and secrets management. For protecting data at rest, data is persisted in the storage layer. We want to look at how we do data isolation and encryption with Aerospike. The diagram you're seeing here depicts two SSD devices physically attached to an Aerospike node. These are physical devices. In this example, each SSD device is also divided into two logical partitions for a total of 4 partitions. So these partitions are logical devices, and data stored on one partition is logically separate from data on the other partition. So remember that one of the scopes that we were able to apply when we were looking at the access controls is the namespace. Namespaces not only provide a scope for the access controls, they also configure the storage layer. That configuration includes which physical or logical device the data is persisted to, enabling AES encryption, and which key is used to encrypt and decrypt that data. So what that means from a data protection standpoint is each namespace provides data isolation from other namespaces. If the user credentials or the encryption key for namespace number 1 was compromised, the data stored in namespace number 2 is still protected separately. So you have that isolation, depending on the use case or the sensitivity of different classifications of data, you can create that isolation. Now, data is encrypted in transit. It's also encrypted at rest using namespace level encryption. So far, so good. So the Aerospike process itself is obviously working with the unencrypted data in memory. So standard OS hardening procedures and system access controls are absolutely critical for Aerospike deployments that store sensitive data. I'm not going to talk about hardening as it's tangential, and there's plenty of industry standard tools and procedures and requirements. And if you voluntarily came to this session, you're probably pretty familiar with those. But I do want to make a couple of points that are related to Aerospike. One, keep Aerospike nodes as a singular purpose. In general, we don't recommend running Aerospike alongside non-related applications, but it's especially important when working with sensitive data. It may be tempting or convenient to run some tools or dashboards on one of the Aerospike nodes, but that just increases the surface area for potential vulnerabilities. The tools or dashboards should not have direct access to sensitive data and therefore should not be running on an Aerospike node. A less obvious example of this would be the Aerospike tools package, which includes AQL, ASInfo, ASADM, and some of these other command line tools that we provide. These are bundled with the Aerospike server, and they are required to be run directly on the Aerospike nodes for a subset of operational tasks. Obtaining and collect info is a good example of that. However, these tools are also a package, and that can be run from a remote server for most of the tasks. So best practice here is to make the Aerospike tools available to authorized users on dedicated nodes specific for that purpose. You'll still want an escalation path that allows for node-level diagnostics and troubleshooting. However, that should be more of the exception and not the rule. The second point I want to make here is about protecting secrets on the file system. Protecting secrets is also a very broad topic, so I'm just going to enumerate the secrets that are associated with Aerospike that need to be protected and a couple of common patterns for how that's done in production environments. So we talked about TLS to secure the network. The private keys for that are secrets. We also talked about the encryption at rest, where each namespace has its own and separate encryption key. Those are more secrets. During an external authentication with the LDAP server that we looked at as part of the access or the authentication, the external authentication, Aerospike is going to query the LDAP server. The Aerospike process has to load the credentials to do that query, and the password in those credentials is a secret. When XDR is being used, it's a similar pattern where the Aerospike process is going to need to load the credentials for the destination cluster. So the username and password, specifically the password, would be a secret if you're using XDR. And then finally, we have system metadata, or SMD, and this is a directory that Aerospike uses internally for various subsystems, which includes the authentication and authorization subsystem. So while this is not a category where you would be managing the secrets here yourselves, it is worth calling out that there is sensitive data in there in terms of that's where the systems store their data. So just in case you're doing anything like root file system backups, or you do allow users in and you're figuring out the permissioning scheme, these should always be protected just like the rest of the Aerospike processes and files. So now with the exception of SMD, all of these secrets are essentially bits of configuration that you are managing. They are keys and passwords that need to be available to the Aerospike process at startup or at runtime. Once those secrets make it onto the server, the OS hardening and system access controls are in place to protect them. However, the challenge lies in managing the full lifecycle of those secrets. They have to be created, they have to be deployed onto the servers, they may need to get revoked, and they will need to be periodically rotated. So this is a problem that's, again, well suited for secrets management tools. So every enterprise security platform has secrets management built in. All the cloud vendors offer secrets management services, and then open source tools like HashiCorp Vault have really exploded in popularity and provide a very robust multi-cloud or hybrid cloud solution for secrets management. So let's look at a couple of patterns for doing secrets management with the Aerospike secrets. The first pattern here is shown on the upper right here of this diagram. And this is basically integrating secrets management into the configuration management workflow. For example, the configuration management tools like Ansible, Chef, Puppet, those types of things can be set up to bring in secrets from the secret store when configuring a node. Aerospike loads the secrets from the file system, and it is completely decoupled from the secrets management system. This has the advantage of being pretty straightforward to set up. There's lots of examples out there, and it's compatible with just about every secrets management tool that there is. However, it does result in any given secret being in two locations, once in the secret store and once on the Aerospike server. So secrets lifecycle management for the Aerospike secrets is a two-step process of updating the secret store and then running the configuration management tool to effectively apply it to the Aerospike servers. The second pattern shown in the bottom half of this diagram is for Aerospike to integrate directly with the secrets management system. However, this would require Aerospike compatibility with a very specific secret store. At this point in time, we're planning on supporting just one direct integration with a secrets management platform, that is HashiCorp Vault. Vault, in turn, integrates with a large number of other systems. It's very popular. And that's an integration that's planned to ship in the coming months, so stay tuned on that. This pattern has the advantage of centrally managing those secrets, and when implemented correctly, it lowers the credential management burden and it lowers the risk of compromised secrets. However, being a direct integration, this pattern does require the secret store be able to meet availability and scalability requirements that the application demands. So that means that this pattern is going to be a bit more complex of an architecture. We're getting there on time, but I think we're going to be all right. Okay, so I'll wrap up with a brief look at monitoring security events and everybody's favorite part of compliance, auditability, which is what the stacks of paper are, because that's how we do it. So the diagram here is depicting an Aerospike node on the left producing a security audit trail and shipping that to a downstream system via syslog. The rest of this diagram is just one of many types of architectures for consuming Aerospike audit logs. I'll talk this one through to give you an idea of what's happening. So first, the audit trail from Aerospike is a separate log from the standard server logs used for troubleshooting and analysis. It includes events that are relevant for security monitoring, such as authentication events and user admin and sysadmin, things like that, and which things are logged can be enabled in the Aerospike configuration. The audit trail is then shipped using the syslog protocol to some type of log collection like syslog-ng or our syslog, the Elastic Stack, Splunk agents, things like that. There's typically a highly scalable queuing system, something like Kafka, in between the log producers and collectors and the downstream consumers. This avoids a tight coupling between the systems, allowing producing and consuming at different rates and independently taking systems up and down as needed without having to coordinate with the other systems. There's also typically events and data from other sources that are being brought in and then integrated, perhaps even analyzed together into whatever the SIM or log analysis platform is. Again, things like Splunk and ArcSight and QRadar and the like. It is in that platform that all of the security data can be monitored in real time to detect and respond to potential security threats or breaches. In addition to that real-time monitoring, this is also where security professionals can look at and analyze historical data to use for forensics and audits and training their machine learning models and things like that. And one final note about this audit trail is that it is possible to ship every data operation, like reads and writes, so that which application or user made which change at what time is auditable. This is a very, very common requirement from the data privacy and compliance side. However, I often find that enterprises make exceptions when the scale becomes impractical for the downstream systems. So imagine an Aerospike cluster handling tens of millions of operations per second in a very cost-effective way, shipping all of those events to a downstream system in real time that isn't designed to scale, doesn't scale linearly, can't handle the real-time ingestion, or isn't cost-effective at that scale. So that's not always the case. It really just depends on what the system is, but it comes down to a risk-based decision that in many cases, organizations instead rely on compensating controls in the application and the system access controls to achieve the auditability of that data access that they require. And I think that's perfect on time. That about wraps up my talk. I know that was a lot of topics very quickly. It's a 10,000-foot view, and there are a lot of details to explore on each of these enterprise security features. So be sure to check out our discussion forums, the developer blog, knowledge base, and the documentation. I'm going to try to hit some of these questions that are coming in. Again, if I don't get to all of them, and even the ones that we do address, we will also put our responses to these in the Slack channel. If you don't know where that Slack channel is, again, it's in the Developer Hub on the right-hand side. And be sure to join us this afternoon for a virtual happy hour after the sessions. With that, let me see what some of these questions are. So would you recommend using AWS Direct Connect for XDR for better privacy? I think I will defer on that one. I'd have to think about that. There's a number of good solutions. What I will say unequivocally is I would not recommend shipping it over the open internet. But there's a number of good ways to have a private connection there. Does encryption impact performance? Yes. So actually, with a number of security features, there's going to be some cost to the security. Encryption in particular. So I did mention that the AES encryption is built into modern CPUs, so it's pretty good, but that's not zero. So certainly with TLS and encryption at rest, there's going to be some overhead. We have found, so you can imagine a write would be more impacted by that than a read, because that write is going to the replicas as well, and each of those is establishing a TLS connection. So there is some performance implications there. It's going to be more pronounced in use cases that are CPU bound, because that's where the work is going to be done for the CPU as well. So it's certainly something that should be benchmarked, and typically customers who are already using TLS wouldn't ever even look at the difference between non-TLS because it's not an option, but we're definitely doing a lot of testing on that and trying to get a good sense of what that difference would look like. What is the overhead of auditing being enabled? So that's a great question as well. I don't have any numbers on that. for the, it's being run in a lot of places, and when you're not doing it on the data operation, I haven't even seen anybody really notice it. With the data operation enabled, it's really going to depend on a lot of factors with what are shown on this last screen here. You have to not only, Aerospike's not only producing all of those methods, so if it's tens of millions a second, the log collection has to be able to consume them that quickly as well. So with a lot of infrastructure in place, it can certainly be minimal, and I certainly know that some customers are doing that, but it certainly, there is an overhead there. Can Aerospike generate certificates automatically? No. So you're bringing your own certificate. Typically, you have your internal PKI, your private key infrastructure that you're using to generate certs. We've also seen customers use some of the public certificate authorities to do that, but it's something that you install on the server nodes, and then they consume them. Let me see the time, we're still good. Is there an event trigger-based generation of audit to be generated? I'm not sure I understand that one. We'll try to pick that up in Slack. And then on the audit, do you have support integration with any tools such as Imperva, Guardium, etc.? So no, not directly, but a lot. This specifically and some other tools were built with those types of tools in mind. So really, take Imperva for example. Imperva just has to ingest these audit logs, just like this sort of ad hoc system that I've shown on this slide here, and that is indeed what Imperva does. So it'll ingest all these audit logs and potentially even connect to some of the other pieces of Aerospike to build that integration. So we've basically built the framework to do those integrations, and we're very interested in supporting getting those built, but it doesn't natively connect directly with Imperva. And what are some of the best practices on following GDPR for edge use cases? That's a great question. I think we should talk more about that. I usually get pretty careful about making any recommendations around GDPR because lawyers have a lot of thoughts and opinions on that. But it's certainly a conversation I think we can continue in the Slack channel if you're there, or in the happy hour later, as I'm about coming up on time. But great question. So thank you all for listening. I know sometimes the security stuff can be not everybody's favorite thing to talk about or work on, and a lot of you who have to implement Aerospike are often just handed a set of security requirements that you have to implement. So I hope that we can help you with that without ruining your day learning about encryption algorithms. Okay, I see a couple more questions coming in. I'll definitely address those in the Slack channel. All right, so thank you, everybody.